Welcome, chemistry scholars. It's Mr. Gopal. Last time we talked about chemical bonding, ionic bonds, covalent bonds. Today we're going to go deeper into covalent bonds. I find covalent bonds to be the more difficult of the two to work on. And that's because in order to achieve the octet rule, which is the rule that the outer shell of an atom that is in a bond pair or a bond with multiple other atoms needs to have 8 electrons in its outermost shell. Okay, that becomes a little bit more confusing in covalent bonds because they share electrons. So calculating the right configuration becomes a little bit trickier. This is part of Unit 4, Chemical Bonding, Day 17, and the purpose is to investigate what multiple covalent bonds are and how we can represent them in what we call Lewis dot structures. Okay, Lewis dot structures, you can see a brief example right here, but there is a problem with this example. We need to draw this a little bit differently so that every atom gets its needs met, okay? And so they come up with this structure, okay? This is like a Lewis dot structure. However, every line in between hydrogen and carbon and the 2 lines between carbon and carbon, each one of those represents a bond pair. So think of each one of those as 2 electrons. I'm going to draw one on there like that just to show you what I mean. So you can imagine there's an electron right here for hydrogen and 1 for carbon. And so you can see from that bond pair, hydrogen is having its needs met because it's sharing its 1 electron and being shared 1 electron from the carbon atom. Same with this one down here. Okay, I'm just going to circle this one. All right. And over here as well, these all fulfill those hydrogen needs, but carbon is still a little bit short. And so we have what we call a double covalent bond between the 2 atoms of carbon, okay? They each share 2 electrons from each of their atoms. When we count it up, we've got, from these 2 circles out here, we've got 4 electrons for that carbon, and then sharing 1 and getting 1 for each one of these lines over here, which means that it gets 8. Same thing with the other inner carbon atom. Let me clear this. And then let's take a look at the one instance that we cover of a triple covalent bond. And that is with an N2 molecule. An N2 molecule is nitrogen, first of all. That's the element involved. And it is what we call a diatomic molecule. A diatomic molecule occurs when we have 2 atoms of the same element that share electrons, hence the name molecule, which stands for molecular bond, which is like a covalent bond. It's a synonym for a covalent bond. All right. We can see here that each individual nitrogen atom has 5 valence electrons, okay? 5 electrons in its outer shell. And so in order for it to achieve the octet rule, 3 of those electrons needs to be shared from each atom. We can see that happening. I'm going to circle it in red here. You can see that happening between the 2 nitrogen atoms right here. Okay, so we've got those 2 on the outside, not being bonded with anything, 2 over here, 2 over here. All right, and then in between, 3 are being shared from the left-hand nitrogen atom and 3 from the right-hand nitrogen atom. So they each share 3 and get 3. That makes 6 in between them being shared, and then they have 2 lone electrons outside that are not being bonded. And that means that we fulfill the octet rule from a triple covalent bond. So as you can see, it's a little bit more complicated drawing these structures and representing a molecular bond accurately. And so in order to do that, I've gone over the steps in a sheet for you. So the thing that I want to go over in this sheet, and you can go back and study it on your own. First of all, I have the octet rule at the top just to remind you. And that the takeaway from this lesson is that the method for covalent bonding should meet the octet rule. That's what we're always striving for when we correctly, I'm sorry, just thinking of 2 words at once, when we correctly create a molecular bond. So if we look down here, I have an example now with carbon and oxygen. So we can crisscross, actually, if we want to do this from chemical formulas, we can use the crisscross rule that we've used with ionic bonds as well and other covalent bonds, simpler covalent bonds. And if we did that, since the oxidation state of carbon is -4 and the oxidation state of oxygen is -2, we crisscross and we get C2O4. We can reduce. We can think of that 2,4. We can think of that almost as a fraction. I'm sorry, I'm going to write this over a little bit. 2/4. All right. And we know that 2/4 from math class equals 1/2. We can reduce that to 1/2, and we don't write the 1. Hence, C2O4 reduces to CO2. All right. And so for the Lewis dot diagram, this is where it gets a little bit more complicated. Now we know, though, what the bond consists of. All right. And we're just reminding ourselves, it's a good first step. Sorry, I'm going to clear that again. Reminding ourselves that carbon needs 4 electrons to fill its shell, and each oxygen atom needs 2 electrons to fill its shell. Okay, and now I like to discuss the idea that the tricky part is that we need to organize the molecular structures so each atom gets what it needs. And the big pattern, as I italicize down here, I'm going to underline it in red. Atoms that need more electrons should usually be in the center of molecular structures. And that is wise because in the center is where they can get the most needs met. They are kind of surrounded by other atoms, and so surrounded by other opportunities to gain valence electrons through sharing, right? And that's what you can see here. Instead of using the dashed line structure, where each line indicates a bond pair, what I've done here is I've used X's and dots, as we sometimes also see in Lewis dot structures. You can see I have the carbon atoms with 2 electrons flanking each side of the chemical symbol. And that's because I wanted to put them in opportunities to bond with valence electrons of oxygen. So I put 2 electrons there as well, because we know each oxygen atom needs 2 electrons to fill its shell. So we're going to need to create a double bond on the left, and then we're going to need to create another double bond on the right. Now, the final thing that you want to think about is that we have fulfilled the octet rule. So we count up everything over here. Double bond gives us 4 electrons over here. Double bond gives us 4 electrons over here. And that means 4 + 4 or 8 for a carbon atom. And now, also, since each oxygen atom has 4 lone electrons that are not involved in bonding, we add those 4, circle them in blue, to the 4 being bonded in red, okay? And that 4 + 4 allows 2 for our oxygen atoms as well. So after some practice, as I say, you can see the patterns, but the good starting point is that atoms that need more electrons should be in the center of any structure that you build. When I say molecular structure, I'm talking about using a Lewis dot diagram to represent the pattern structure when covalent bonds form between nonmetals. So you can use this. I'm just going to clear this here. You can use this in order to help you navigate the lesson. I hope this has been valuable. When you look back, what you're going to do is try to apply the logic in my example to coming up with a bond for oxygen. I'll give you a hint. We know that oxygen has 6 valence electrons, so we want to think how many more does it need? Therefore, how many bonds should be forming in the center, right, in order for it to fill its shells, all right? Down here, we have C2H2, and we know that hydrogen needs 1, carbon needs 4, okay? So we have to be very careful about the way that we fill that. Again, carbon should be in the center because they need more. And then finally, we have carbon monoxide, all right? So how many bonds do we need to create in between the carbon and the oxygen atoms so that carbon gets 4 more and oxygen gets 2 more? I hope this has been valuable for you, watching me put together CO2. And good luck with this. Don't give up. It's very difficult, but I'm sure you'll get it. Just try to stick to the patterns and way of doing things. List out how many electrons in the outer shell each element is lacking and build your bonds accordingly. I hope this is valuable. Take care, and I will see you soon.